Welcome back. We're now going to dive into Module 2 in this series on getting started with the Electric Drives Demonstration Platform, or Eddp. This module will introduce you to the kit itself and introduce some of the tangible ways you can implement the ideas we discussed in the last video. Be sure to go back and check out Module 1 if you missed it. Now, let's get started with Module 2. What is Eddp in its physical form? It's a platform composed of an RDZ7 control board, a power stage board, and an Ethernet interface for connecting to a PC, which is of course sold separately. The kit is available from a Xilinx partner in Germany, Trends Electronic. If you get the full kit from Trends, it comes with a 15-watt brushless DC motor, but other motors can be used. The power stage supports up to 1 kilowatt. The RDZ7 is a ready-to-use development platform designed around the Xilinx Zynq 7000 all-programmable system on chip. The Zynq 7000 architecture, which is the first generation of the Zynq SoC product line, tightly integrates a dual-core ARM Cortex-A9 processor with Xilinx 7 series programmable logic. This pairing provides the user with the ability to surround a powerful processor with a unique set of software-defined peripherals and controllers. All this is tailored by you for whatever application you're planning to conquer. The design process is very straightforward and provides a systematic path starting with defining your custom peripheral set all the way to bringing up a Linux operating system running on the processor. The power stage, or EDPS, has two current sensors, two sigma delta 12-bit analog to digital converters, or ADCs, for the motor currents, plus one for the motor power supply voltage, and an interface for the incremental encoder. The power stage can accommodate up to 50 amps, set to 25 amps by default, and works great up to 48 volts. On the next slide, let's look at the Zynq SoC in this application. To appreciate the advantages of a Zynq SoC, let's think about one hauntingly familiar scenario. Your head of marketing wants you to rejuvenate your motion control platform because of Industry 4.0 pressures, and competitors are quickly gaining market share at your expense because they offer industrial IoT-enabled products and your company doesn't. Additionally, marketing wants Linux because it's open source, well-known, and immediately connectable to the internet. And of course, the same marketing wants you to keep the performance of your current drive intact so that the actual customer base is happy. Unfortunately, this clashes with Linux because you developed the control portion with an RTOS. As a designer with forethought, you'd like to keep a single processor using Linux, but separate out the control aspects such that a failure on the Linux process does not affect or impact the control in any way. You'd also like to keep most of the control you've developed over the years, but you need faster pulse width modulation, PWMs, and assisted ADC conversion such that the load on the processor is minimized. You also want to extract data produced by the motor in the Linux environment without impacting the control algorithm itself in any way. The Xilinx recommended approach is to consider partitioning the problem into two parts, using the processor system, the PS, and the programmable logic, or PL, such that you benefit from the application processor when it comes to Linux and communication, while the control is executed in the PL. This is exactly what Eddp does. Let's take a look. While you're likely familiar with developing using an embedded processor, possibly in C or C++, you might be new to heterogeneous computing, such as using programmable logic. Don't be worried that it requires a whole bunch of significant new skills, as this just isn't the case. To appreciate the advantages of the tools available and at your disposal, let's take a look at the field-oriented control algorithm developed into Eddp. If you're familiar with motor control, you'll recognize a set of functions within the overall algorithm: Clark transform, Parks transform, PI controllers, PWM encoders, and current acquisition. So check this out. The algorithm is fully implemented in programmable logic with C++ functions. How is that possible? The entire Eddp design is based on Vivado HLS, a powerful productivity tool from Xilinx that is capable to read annotated C or C++ and create RTL code, or the traditional languages used to design with FPGAs such as Verilog or VHDL. This can then be input into the Xilinx Vivado tools to produce the programmable logic bitstream file. You then combine this output of Vivado HLS with Linux and you get the controller deployed into programmable logic. It sounds easy, and it is easy, following the instructions of the next modules. Before we go further, if you'd like to keep most of the control you developed on previous processors, assuming it's been developed on C or C++, and you do not want it all in the PL, you can use Linux on one processor and bare metal in another, as described in Xilinx Application Note 1078 or XApp 1078. There's also a wiki.xilinx.com where you can search for the latest information around XApp 1078. But this configuration does not come out of the box in Eddp, and it is not currently supported. Eddp focuses on a bimodal approach, Linux operating system paired with the PL. This configuration would imply a trimodal approach, a Linux operating system, a bare metal system, combined then with the programmable logic. Having said that, it should be pretty easy adapting the current Eddp to this type of configuration. Getting back to the topic of Vivado HLS, it's important to build up an intuition of how your C or C++ is going to look when implemented in the PL. As you can see, it does indeed align with the description of your algorithm, in this case the Parks transform, and it's then compiled as a library module that can be imported into the Vivado IP integrator for interconnect with other modules. This approach is consistent with typical model-based design using a graphical tool. In this particular implementation, the Parks transform is realized with integers, but there is no limitation using other data types, such as floating point, for example. The whole design is then contained in a set of interconnected components as described in the block diagram, and it ends up being a design module that you can instantiate 1, 2, or any number of times in the PL, constrained only by the amount of PL you have in a particular device. This is a key productivity aspect of this flow. Here's a more detailed view into the flow of Vivado HLS, and you can see Vivado can pull in a design from MATLAB Simulink using Xilinx's system generator tool as well. This is yet another path for making sure that model-based design and HLS design can work together. Multiple boards are available to evaluate this design methodology. They were introduced and available prior to the arrival of Eddp and carry the compatibility requirements of having dual PMOD connectors, a Zinc 7000 on board, and having been tested for proper functionality. Another approach, which is fully representative of an even higher level design of an electric drive, is written as a single C or C++ function. It uses the Xilinx SD SoC tool for creating the full design and its data movers. This alternate approach is available on the GitHub site as well. SDSoC is different from Vivado HLS because you give it a full algorithm description, not just a module or a function. You're free to modify the example design on GitHub to tailor to your needs and to evaluate the design methodology. If you're keeping score at home, we've now covered 3 high-level flows for designing with Xilinx that don't require you to have the expertise of a traditional FPGA designer. Vivado HLS, we briefly mentioned system generator, and now we just highlighted SDSoC. Taking the motor control design to the next level, you can integrate multiple access control into a single device, thus creating a compact, reliable, and safe drive system. Performance increases, power decreases, and overall cost of the system decreases as well. Anytime multi-access drives are mentioned, the topic of functional safety is typically brought up as well. As mentioned, the key element of modern drive systems is to be safety capable, meeting the IEC 61508 requirements. Xilinx provides the foundation to design safe drive systems. Zinc SoCs enable SIL 3 certifiable systems with a comprehensive design and safety package that includes device support, certified tools, and a complete documentation bundle. You are fully equipped to design robust control for safe drive systems. Xilinx devices are highly reliable and enjoy extensive availability over the typical life cycle of industrial assets. This is critical for electric drives, since we supply to multiple other long life cycle and market segments, such as aviation, military, and medical, to name just a few. It's an attribute you can count on from Xilinx. Products typically have a life cycle of 15 years availability as a bare minimum. Most times, they're extended well beyond that, with formal last time buy processes available as well before a product goes end of life. Aside from commercial availability, industrial and these other markets demand extremely reliable devices throughout their operational life. Xilinx addresses these needs with stringent qualification standards of the highest order from introduction to end of life and make all that data available publicly. Many customers of ours have referred to Xilinx as a gold standard in this respect. Lastly, the capability, flexibility, and scalability of Xilinx solutions are further augmented by our partners in the ecosystem. For example, Qdisys, based in Verona, Italy, has developed multiple drive solutions based on Xilinx devices over the last 10 plus years. Known for their IP cores, they have built drive solutions such as a 3-level inverter motor control design. This design has been acclaimed for its capabilities of control and sophistication that can be achieved using silicon carbide and the methodologies shown so far in this video. That's all for this video. Don't forget to check out the next module. We'll shift from theory to walking you through everything about the SDSoC build of the field-oriented control design using the Eddp. We'll be covering everything from obtaining the source package to modifying code and rebuilding the FOC algorithm so you can follow along with your kid at home.